one of the things that really stuck with me in my formative years is my dad's like, if you're going to do something, either be the best at it or don't do it at all. But give
Uh-huh.
it everything you have. It deserves an honest chance to make it completely a good shot. I knew for me to make any space for myself in this room, I'll have to try it where like there is some learning areas. I decided to pursue education in US, which was also like another uphill battle because now I had to convince my parents to leave the country. They didn't even have the visa at the time.
Hi, welcome Shreya to my Startup Founder podcast. It's a pleasure to have you on. It's good to see you since we met at the rooftop networking event. Hope you've been doing well.
Yes, thank you so much for having me, Brandon. It's been great since I'm looking forward to our discussion today.
Yeah, yeah, absolutely. And of course, as we spoke about last or a few weeks ago, you're working on propulsion or a propulsion system that you're selling to various companies that might need that, which is a fascinating area to be in. Of course, there's a trend going on now where people are moving on from AI and software into the physical domain, like robots and building things that do things in the real world. So it's exciting to talk with someone that's working on something like that. But before we jump into that, do you mind just explaining a bit about your past, what led up to this? You started this venture. What's your background?
Yeah, absolutely. So I think I'll start with my undergrad because that was quite the pivoting point. I actually moved to US and pursued my two engineering degrees. I graduated with mechanical and aerospace engineering from University of California, Davis. And while I was there, I also got to work in an advanced composites lab. That means from freshman year onwards, I had hands-on experience and working with diverse projects with both Department of Energy and US Navy. And even as that project built on, I got to work with more composites structures and kind of grew my expertise over the years. I also got licensed as a pilot, which was my lifelong dream.
Ah,
So
nice. That's awesome.
through and through aerospace enthusiast, I knew like I'm going to build in this domain, I'm going to do something in this domain. Like that clarity I've had from the get-go. I just didn't know, I couldn't localize like where I wanted to put my like potential to use. And that's why I tried everything that I could. So everything from CubeSat, satellites, aircraft systems, rocket propulsion. I tried everything to understand where my strength really lay, like, worked in compatibility. And I thought like process of elimination would be the best way to go through it. So I tried everything. After finishing my undergrad, I actually got brought on for a NASA project where we were developing new astronaut spacesuit material. It was a collaboration between Georgia Tech, NASA, and us. And through that, I actually got to build something really cool for the composite industry. It was the first time that you could actually map the damages within a body, which is not true. It's a big milestone given in metals, just for context. You can see damage visibly, you can actually map it in a different way. And there's a lot of testing processes that you can use to do that. But in composites, the linearity to do that exercise doesn't exist. And you can't even know when the composite will really fail you.
Do you mind just explaining what exactly falls into the definition of a composite?
Composite structures are non-metallic structures, more like polymers, where they're
Okay.
like fabrics that are strengthened with bonding adhesives. And together they harden to become something that can compete with metallic structures in a very simplified manner.
Okay, so you're saying there's a way to see like the stress and strain, the wear on metallic structures, but not so much on the composite material side.
I mean, you can, but it's not easy to do so. Like you have to
Okay.
break it in order to be able to see it. Whereas in metal structures, you can see deformations right away on the structure. Whereas in composite structures, they will completely reach the breaking point before you'll ever know that they are breaking.
Ah, I see. I see. That makes sense to
Right?
me.
Have you ever seen those dog bone samples that people stretch to like pull apart, and then you see the neck area kind of like narrows out? So
Right.
you know the kind of elasticity and the mechanical properties that the metal carries, right? When we try and do the same with composites, it doesn't exist. It literally just fractures. So
Okay.
that's why it's very difficult to know when they will really break. So that's why this was such a big milestone, to be able to not only tell if a composite will fail, but also 3D map it, the intensity of its damage. So those were the milestones. And then that project was then picked up by Department of Nuclear Energy, and they've been using it to do testing there. Like that's where, but because COVID hit around 9 months into this project, and that's when I had already done most of the work. We were just writing a whole lot of papers, and I realized like I wanted to do something more as well. So decided to move back to India, which was a big decision. And honestly, it's like my adult life had been stateside, and I had to uproot it
Okay.
all to move back. And I moved back to India, and I actually moved to a city where I knew nobody. I didn't even know the language. I just showed up, and I had put out a feeler through that one friend I had stayed in touch with in India. And she had a friend of a friend who had like a flying taxi company in India. And so I got in touch with them, and they were more than happy to have me on board. So I joined them as a program manager. And then while I was there the first year, I was at their institute. IIT Madras is like it's like equivalent to what MIT is in US. It's like the highest ranking like technology institute in India. And so when I moved there, like, of course, we were solving a lot of different problems, but more localized to like Indian terrain and Indian operating temperatures. And that's the first time I really understood that the global supply chain of all the parts that we were building with was centered around a hobby domain. So now that's the real main crux of the problem, right? Like we are trying it worldwide. Even though in India, the drone ecosystem started out like say in 2021, the ecosystem for drones has stayed on for like past 30 years, has been like going through multiple iterative cycles across the globe. But in India, it was the first time they were actually building, and within like the first year, they had over 600 startups. Like it's insane to be in India. It's so dynamic and so fast paced. Like technology is always evolving. So I really wanted to be in that space that was like, turning things very, very quickly, and also be part of the process in a meaningful way. And that's the first time I understood that if we really wanted to build systems that would kind of like pivot how we look at air travel ahead of us, we need to do it with systems that'll support that, right? And then I asked myself that question: given what we have today, are we able to build those systems? And that the answer was no. Given they were all off the shelf solutions built for a hobby ecosystem, right? None of them really wanted to materialize it as a commercial ecosystem where there is like operating cost, there is unit economics of each flight, there is also like maintenance, repair, overhaul, and complete understanding of what goes on in owning an entire drone or even a mid-size aircraft. Most folks are like happy to just be able to fly, right? Nobody was really thinking like, oh, I want to be able to solve tangible problems now, like search and rescue, like healthcare issues, and like, transportation, ambulatory support. All of these things, like these are real world problems now people are looking to solve using a medium of a drone or like a UAV or a flying taxi. And that's the first time I realized that, okay, if we want to change all of this, one, it needs to be like next generation, but also it needs to be able to unlock at scale. If it is still at a prototype level in a lab where only few people can tap into it, that'll just make the unit economics of flight not work out at all, right? So from there on, we started. I started out in like October of 22. Literally, I didn't even finalize. Like when I left Chennai, I just drove down with everything in my car, and I drove down to Bangalore, and I was like, okay, we are building here. And I'm in 3 days, I figured out a place to rent. I didn't even have a hotel. Everything was just on the go. I was just determined to get started. Basically, I'd made up my mind, like, and I feel like a lot of people like plan these things out, right? But for me, one of the most determining factor was like, if I'm going to do it, I want to do it right. And my family background is primarily in manufacturing, so I grew up watching how things are manufactured, and I know how like the design teams work with the manufacturing teams. And given my background, I felt like I was positioned well to take on this challenge, right? Like for the first time, it was exciting to just push that boundary, what people had stagnated over the past couple decades. Because the only competitor I see, the youngest competitor I have right now, is a 15-year-old company. Like that's almost a decade over. So that means like I'm ready to disrupt the market with new products, and the timing is ripe. It seems that the world everywhere wants to commercialize their operations. Everybody has started using products in a way that they're trying to understand what is it that will truly unlock the unit economics of flight.
So you mentioned that you always knew you had this clarity that you wanted to go into aerospace, which is a great thing to have. Of course, if you know what it is that you want to do, then you can focus all of your time into it and specialize in that area and really become an expert in it. So it helps a lot to really be a domain expert. So that's great. And then you also tried out various areas within that space to see which matches your talent. So that's also an important thing to play to your strengths. So I'm feeling optimistic already about your plans here. But I was curious though, what led you to what sparked that passion for aerospace? I know you said that you had a manufacturing background, your family. Did it come from there? Were you guys manufacturing something in aerospace, or is there some other inspiration there?
So actually, I my dad is like a first generation of like a self-made man. Before this, my
Okay.
like grandfather was into farming, and we are from a tier two city in India, where I was like about 7, 8 years old when I told my parents like I wanted to do more from my life, and I didn't see that happening if I continued to stay on in my
Yeah.
city. And as an 8 year old, I literally had this discussion where I pitched it to my mom and then to my dad that I
Uh,
need to get out of here. And I insisted I be sent to a boarding school.
oh wow.
Yeah. So I actually chose, so it was hard because my parents, they've never stepped out in that way. And to them, sending out on a limb their kid like with no support was a big deal. And especially like you have to understand women in India are positioned differently at the time as well. We are talking like early
Okay.
2000. The staging is far different. So for me to even say I want to leave the city is a big deal. And then the
Right.
fact that I have to go. But for my dad, the hardest challenge was he's like, when you'll grow up, like it's like you'll be in boarding school, then you'll go to college, then you'll get married, and it's like I'll never have you. Like, your formative years are meant to be with your
Yeah.
parents, and then like he was really struggling with that. But I did convince him that look, I feel like I have some potential and I can truly unlock it in an environment different from this. And whatever convinced him there actually then pushed him to embrace the whole setup that I really wanted to push forward for. And they come, when I say manufacturing background, they do hotelware. So they do stainless steel. My dad does a lot of like glassware, earthenware, not earthenware, but like wood and all the hospitality industrial work, right?
Right.
They do a lot of the manufacturing for those setups. And we used to export. So like every summer I came forward after that, I would spend it at the factory, and like I grew up watching the workers and the employees like really like enhance their art. But also I understood like this is something we need to get ahead of. Like there's a nuance to it, but there's a quite the balance that you need to be able to work around, like building a robust system and building repeatability. That balance needs to be done in a quite the like an optimized way. And that's how I started honing that skill of like managing the floor and all of that. So I kind of grew up watching all of that, the unit economics that goes behind like pricing, and being able to understand what are the different methods to deal with sheets and different cutting. Like these are mega structures, you're talking like good big like bowls and everything. So there's a lot of thought process that goes in there, and they're pushing out like say 100 200 pieces a day. So it's a pretty scaled up project. For my dad also, he has no background, but he figured it out, right? Like he figured it out on the ground. So I knew like when it came down to it, I will do something bigger in
Yeah.
manufacturing. So I think that's how it started. But then like when I was in my boarding school, I one of the things that really stuck with me in my formative years is my dad's like, if you're gonna do something, either be the best at it or don't do it at all. but give
Uh-huh.
it everything you have. It deserves an honest chance to make it completely a good shot. Because if you're spending the time of your life on it, then you should make it count, right?
Yeah.
So the boarding school even that I went to, right, it has a very, very tough acceptance rate. As a 9-year-old, I competed with over 300,000 kids, and only
Wow.
52 of,
Wow. Only 52
yeah,
accepted?
yes.
Yeah.
So that was a
Yeah.
really big deal.
Yeah.
Like,
Yeah. It's amazing.
so once I knew like all of, and after that, I also knew that opportunities can come to you, but at the same time, you should be courageous enough to take them on, right? So I when the next stage came that, okay, what is it that I really want to do in our ninth grade? We just start deciding it. I didn't take it as seriously, but I just knew that I wanted to like build the fastest thing or fly the fastest thing. It started there. I just love,
Interesting.
yeah, the speed of things is what really drew me to the aerospace industry. And the fact that I was like, okay, I'm in India for Air Force pilots, there is a physical limitation, and I fell short in height, quite literally. So I was like,
Uh,
okay, I'm gonna build planes
yeah.
that I can fly. I was like, you
Right.
know what? I'm gonna do it. I'm gonna do it in my life. Like I'm gonna build planes that I'll fly. And
Yeah.
that's how I
There's no
really,
height requirement for building them, right?
yes. So I was like, I'm gonna build one that flies and I'm gonna make it super, super fast. So that's how it started, that I'm gonna do aviation industry. And in India, I don't know if you've looked, but a lot of the opportunities don't exist, right? Like even the Indian space program is more focused in social welfare programs, and not like just to like prove concepts as you would see with a lot of other space agencies. It's more driven by like doing social. I don't know what the right word would be, but like it needs to be able to support the industry, like the welfare of the people, basically.
Right. Yeah. Yeah. I see what you're saying. Less about the research and the technology, more about the social welfare, which I get from a government perspective why you'd want to orient things like that. But in the long term, it does pay off to do deep research as well. So,
I agree. So, but a lot of the government, a lot of the funding comes through government, right? So then the
yeah.
space program was justified only for social welfare. It was never for like research focus, which is the turning point we are seeing now. Like a lot of the industrial partners, both private and public, are like moving and getting towards like having advanced systems and pursuing research in very niche areas, which is great to see. But coming back, like at the time when I was looking, there was no opportunity, right?
Yeah.
And so like I knew for me to make any space for myself in this room, I'll have to try it where like there is some learning areas. I decided to pursue education in US, which was also like another uphill battle, because now I had to convince my parents to leave the country. They didn't even have the visa at the time. Like my parents, like they literally could not come to me if they wanted to. So I
Okay.
came as a 17-year-old all by myself.
Oh, well, and did you know English already at that point? Did you grow up knowing English?
We're bilingual here. I grew up
Okay. Okay.
knowing.
So you grew up. Okay. Yeah. Yeah.
For my parents, it was more of a concern from a safety perspective. Like, say something happens to me, literally, there is nobody to come down to help me. From
Right.
their perspective, it was a very fair point, which is when we had like one of my relatives who was there, and my parents' only condition to move to US, like for me to go to college in US, was that I find a college near them. They didn't care like if the
Yeah.
program is great or like the education is gonna be awesome or whatever. Nothing. They just
Yeah.
knew it had to be in their vicinity. Like if something happens, they should be able to come to me very easily.
But you ended up going to California, right? Or
Yeah, so they were placed in California. I chose UC Davis. I didn't even know Davis. Like honestly, I just
yeah.
showed up. I was like, for me, being able to show up is the biggest thing of it all. Like I will
Right.
figure out everything once I'm there. And incidentally, once I showed up in Davis, 3 months later, my cousins moved back to India. So
Oh, so you had planned to were your cousins living in California, and then as
they
soon
were
as you
working
went
at
there,
Apple at the time, and
oh,
then
okay,
yeah, and that was the closest. I didn't get in through Berkeley, so Davis was the closest one next, and then
gotcha. But then they moved back, and then so now you're all on your own
yeah.
at Davis. And is that where you learned? Um, were you studying aerospace there, or yeah,
Honestly, I didn't know anything about Davis until I showed up there. But the more I stayed, I think unknowingly it was one of the best decisions of my life because of where I was, I actually focused more into tapping into every opportunity that I wanted to. I made it count in a way that I didn't think I would ever make those 5 years count. I tried everything I wanted to do. I learned new languages. I learned fencing. I learned horse riding, but I also did like advanced composites in a research lab. I also pursued my flight school. I also attended school. And then I also like attended like varsity hockey team. So all in like I had a very fulfilling 5 year experience in college and I made great friends. I had great support from my professors as well, which is something I truly like value the most and has been the biggest turning point of my career. I think in India, I had gone with the mindset that at the boarding school, because it's meant for women, I'll be able to, like, just like I went to a women's boarding school, there is like a boys' boarding school as well. And there they were taught like virtual trading and they were taught aero modeling, which is what truly drew me into the whole program of going to a
right,
boarding school.
yeah,
But then when I went to the girls one, it wasn't quite that, right? And I didn't know what were the right avenues to truly understand my potential. And when I came to college, by then I was just like, I just need to show up and I will figure it out from there. But I think my professors truly helped me understand that your potential is something you should keep pushing. You don't know the true limitation of it until you push that boundary, right? And that's the first time I truly understood that I'm only as big as how much my brain tells me to be. So if I want
yeah,
to reach out there, however far I want to go, I will go wherever it is. So
yeah.
it's me who's setting the boundaries ultimately. And that like was a big turning point, and that's when I decided like, okay, I'm going to build, but let me learn all the things I need to do, build all the experiences I need to, so I can actually build an ecosystem when I come back.
Yeah, yeah, no, thanks for really painting this picture of your background. I mean, I can feel the ambition, the motivation of just I mean, most 9 year olds, uh, usually it's the parents forcing the kids to go to prep school, to boarding school, and then the kids going and being homesick. But for you, is the opposite. You're really pulling away and having your dreams and ambitions kind of pull you through this system, even though it wasn't clear exactly what the exact path was. But I'm glad that you made it to Davis and tried many different things and were able to find your path towards aerospace. And so, what made you decide to move back to India to start that company? And then, just if you want to start going into what is the company and what's the main product, the main goals of the company?
Once I moved back, I think COVID was a big time for me to reflect on like what I really wanted to do with my life. And that moment of clarity came that I actually enjoy taking on very challenging like projects, right? I
Okay.
like it when like where people have really I guess I get my adrenaline rush when I can build something beyond what people have already done, right?
Yeah.
Like that's what gives me my thrills. And then so once I moved back, I felt like flying taxi was that answer. And then there I realized actually there's a bigger game at play, where I understood that once I'll give you a little bit example of how why I chose India, right? If you think about it, like worldwide, everybody looks at adaptive rate of any new innovation, right? Like you've built something great, but is the masses going to really adapt to it quickly? And
Right. Yep.
that appetite for something new is something I felt was not seen at like looked at very clearly when it came to India. People always think that like in India people want to take on opportunities that have already been tried and tested before out there. Whereas in India, over COVID, what we saw was that people who had no idea how to even do credit card or digital payments were now running businesses over digital space, right? Like everybody, I'm talking even a coconut vendor who's sitting off the side
Yeah.
streets, right? He's like doing digital payments. For me, like growing up, watching that change come into play within like a matter of months has made me realize that India has that appetite. So given the right technologies, it can really upstage itself. And for me, coming back would be like bringing back the whole circle from where it started in some ways. So
Yes.
one was that, and two, like I also felt like because things were not as defined here, I could bring out more new innovations that were befitting the setting here, as opposed to bringing what was done like in US and in Europe. Things are more structured, so when you bring it down in India, that structure is not followed as is. It
Hmm.
gets adapted in its own way. But here, if we start out from ground up, then it can be followed in a manner that can be truly befitting the area it's built for. So that's the mindset I came back to build with. And hence when I started, I was like, it one two things were clear. One, whatever I do must be scalable. I absolutely would hate for anything just to be lab size.
Yeah.
Like it cannot be just a prototype.
Right.
I'm not
Sure.
expert in just building prototypes. For me, it has to be scalable from the get-go. And with that mindset, I actually tied up with one of my friends who I met while I was working at the flying taxi startup. And he was actually the architect for the entire program. Like he's the one who designed everything. And he too felt that if we do this, we can actually help unlock a bigger stage for everybody who's building in this ecosystem. So together we started, and it was just the two of us for the first 4 months, where we
Uh,
did and we have no experience building a factory or like a class 1 class 10 clean room or whatever. I literally just read from my previous experience, built an entire space, and now we've gone on to build two other factories, right? So it's literally the first factory we built was meant to be efficient in terms of production, but also R&D, which are two opposite things.
yeah.
If you think about it, like R&D is more about like getting the job done with whatever it takes, whereas production is the nuances in being able to repeat it 100, 200 zillion times, right? And the
Right. There are a
quality
lot
check.
more constraints on it versus research. It just can I do this, and then manufacturing. Can I do this efficiently?
Exactly. So first idea was like, okay, how do we get this going? And then we had our first big through at 7 month mark, where we had built the factory in some sort of like, a makeshift way. We were already testing while the production was underway. Like on the
And
side,
sorry. So this factory, is this to make the entire flying taxi, or is this just one component of the taxi that you're building at this point?
we actually started out thinking we'll do one component at a time. And
Yeah.
then based on different systems, we would either expand or like divert to another product line. Like
Right.
we hadn't decisively, we wanted to see how our product would be taken in by the market. We kind of understood that propulsion system is the one that's actually defining what the unit of each operation looks like, right? It boils down, even in terms of maintenance, we studied the parts that needed to be replaced the most. We studied like what is it that's truly defining how much endurance you're able to tap into a flight, what really helps unlock at different stages. For each application, the answer came down to how long the flight was, how fast the flight was, or how long the entire operation was. So that means that primarily the propulsion systems, even though not critical to communication or security, it was critical to the operation segment, to
I
the
see.
point that it was defining if people were able to fly at like higher altitudes. I'm sure you're aware we have like the coldest regions and the hottest regions in India.
Yeah.
The operating temperature range is widest. It's a technical nightmare to work with. Plus, you have heaviest rainfall. You have a dry desert on the west. You
Yeah.
have heaviest rainfalls in the east. In the north, you have the Himalayas. The terrain is hitting mount like it's insane. You're at sitting at 6,000 plus meters. There's a whole lot of things going on, and then the only thing that's going to get you through is a very robust propulsion system, because India does have to like our initial program was to work with a lot of the Indian companies, and their biggest pressing point was being able to patrol the border areas. So we
Oh,
have
I
in the
see.
north, they have the coldest regions, and then in the west they have the hottest regions, which is like the desert area. And then you have like, we have a very vast coastline, which is completely open-ended. So it's very humid and corrosive in nature,
Yeah.
right? Temperatures go upwards of 45 degrees in Chennai, where I went the first time. Like my landing time was, when I landed at night, the temperature was 33 degrees
Oh, wow.
Celsius. I
Oh,
wanted to
okay.
sit
Yeah.
in the plane
Very
and
warm.
go.
Yeah.
It is pretty.
So you decided to focus on propulsion. You looked at the benchmarks that people in the industry look at, such as flight duration, the temperatures, all these different constraints, and realized that operationally the propulsion system is critical. But what kind of propulsion is this? Is this like a propeller, jet propulsion? What kind of propulsion is it, and how did you decide on that?
So we looked at what the world is moving towards next, right? A lot of the
Yeah.
folks want to decarbonize. A lot of the bigger companies have their missions outlined to, like, reduce their carbon footprint or like make it negligible almost by 2050. So a lot of people are looking at electrification or like hydrogen systems. And from there, we decided we'd do propellers, BLDC motors, controllers, and hydrogen fuel cells. So that is the entire module that we set up for. And we have a staged category of it. Our vision is to not only make the hardware but that is robust and long lasting, but also make it smart in some ways, right? And what I mean by smart is it should have like preventative and reactive maintenance on board as well. And we can do that through multiple channels, and even by having a sensor stack on board that does give you live data constantly. Very simply put, it's like today, if you own, say, an aircraft, which is an asset that can give you about 1,000 hours of service, you're required by laws and policymakers to have it checked at every 100 hours. Then even the downtime of it is like bleeding money, right?
Right.
Ultimately, every time the aircraft isn't flying, it's bleeding money.
Yeah.
And if you look at it from that perspective, the logistics, sending it for an A&P mechanic check, all of that is an average cost of like 5,000 plus dollars. So imagine you have to do it at like every 100 hours. For 1,000 hour service, you're already spending like about $50,000.
Yeah.
Whereas if you look at the kind of system we want to build, not only does it offer you superior performance, but it also advances and quadruples the life of the hardware systems, which allows you to then push that 100 mark to like say 200, 300 mark. Now you
Wow.
are
Yeah.
able
That's
to
great.
reduce the cycles of check. That is one, but also it has a sensor stack on board that'll give you data continuously. So first stage is to build the hardware, get it tested. And the way aerospace industry works is like the moment we have systems that are there, as long as, for any policymaker, the interest is to ensure their safety as the foremost concern. So as long as you're pushing the boundary for safety higher, they are
Yeah.
more than interested to work with you, right? So the aim is to make very, very safe systems such that you can not only have robust performance and like long lasting product, but also live data that can tell you, okay, yes, you need to go for a maintenance check now, instead of sending it every, like, to the A&P mechanics. What they look at, that sensor stack would do just the same
Yeah,
actually.
and so it's not even just the literal propulsion, but kind of a whole system around a propulsion system that includes. You said what, the fuel cell motor? What kind of motor was that again? You said
It's a BLDC motor.
the
So
LTC. Yeah.
there are multiple kinds of motors, but we chose BLDC because of the kind of torque and RPM performances we cater to in this segment. And
Okay.
essentially it allows you to have what we have really unlocked with each. So we've done monolithic carbon fiber propellers, BLDC motors, and
Okay.
FOC controllers, and now we are going to launch the hydrogen fuel cell. The previous three in itself are big milestones, given the industrial standard so far has been to build composites that have like multiple things in them. Like it's not just carbon fiber, you'll have foam inside it as well to reduce the weight.
I
Ours
see.
are monolithic carbon fibers so that you can tap into a wider operating temperature range. But we can now tap into very diverse profiles as well. I'll show you.
Yeah, that'd be
I do
great.
have it with me.
Oh,
So,
nice. Yeah,
so this is a 34-inch. So this is pretty
that's
big,
great.
but
Yeah,
so this is a 34-inch propeller. If you see, right, like it's a, I don't know, you can see the profile is pretty thin, but it's
yeah,
designed much like a bird's wing,
right.
so that you can get certain amount of like lifting capabilities on the get-go, and you can get at lower RPM. So we understood like how does the profile look like. We studied that, and then understood that takeoff and landing are like power dense but short segments of the profile. The cruise is the longest segment of the profile, which is where we really want to be lean and clean. What I mean by those two is that you want lowest RPM with the highest thrust. That way, the energy consumed to do the operation is very minimal. The energy
Okay, I
consumed,
see. Yeah,
ultimately, it's the game of how much energy you're consuming for each segment, right? We already know that for takeoff and landing, it'll be very, very energy heavy. But for the cruise profile, if we can lean out that process, that's the one stage we have really worked on and been able to add a 5 to 8% efficiency gain just in the propellers change. So if you change one of ours with what exists, you can see about 5 to 8% efficiency gain. We've done pilot with over 25 companies, both in India and in US and UK. These are the three areas we've run pilots with over the past 9 months. And we've had really good feedback cycles where people have tested it in very different applicational scenarios. They've actually tested it with pebbles and all of those things. So the ruggedness, think of it this way, your propeller is the only thing exposed to the weather extremities.
mhm.
Everything else can be covered within the body, but your propeller is the only thing that's always going to be exposed. And where we've really pushed that limit is we've introduced something called passive de-icing. What that does is, if you see here, everybody who's building these smaller systems is fighting for every gram they put on the aircraft. So it's
Okay,
a fight between, you're triangulating trade-offs not just in terms of weight, cost, and power consumption. So you have to now fight off, you can get best of two. You can't get all three. That's the challenge here.
right, right.
So you're almost always trading off one for the other two, basically.
How do you even design a hardware product like this? I have more of a software background. I get, you iterate things, you try them out, and you can quickly update them. But on the hardware side, I mean, do you start off, you mentioned it's similar to a bird's wing. Do you start off with some certain foundation that you learn from school and then kind of build up from there, or, chisel off here, build up there on the blade? Or is it like, are you simulating things first and then once you have a good idea, okay, this will perform well, then manufacturing it and testing it out? How does that process work?
So there were two separate things, right? First is like being able to design something, and then we see the manufacturing feasibility of that design. Those are two separate things.
Okay.
And when we start, our biggest epiphany was like being able to manufacture in this format because of the manufacturing style that we stumbled upon after a lot of testing. We
Uh,
realized now we can truly unlock multiple shapes and profiles, which is not true for the rest of the industry. And that's what's really given us that edge, because now we are able to do composite solutions that are agnostic of size and scale and shape. And if I show you a competitors, right? So
yeah.
in their design, because of the foam inlay in the middle, they're constrained to a certain profiles only, because there's a way you can manufacture it, and that has its own limitations.
Oh, so your adaptation to if I remember correctly, it said you adapted to have the no foam within the blade in order to adapt to the weather. But then it
Yes.
turns out that that's actually also making the manufacturing easier. You're saying?
Yes. For
So
in
that's
our
a great
case,
adaptation then. Yeah.
and in composites, there's no linearity in size. In metal, if I make a small piece and I make a big piece, the metal properties transfer linearity, right? In
Okay.
linearly across the board. Whereas
Uh,
for composites, that's not true. And that's where our expertise really helped. So if I
yeah.
show you, this is how competitors looks like. It is fairly flatter in design.
Yes. Yeah.
I don't know if you can see it, but the curvature is not as steep as ours. It's fairly flat, and that's because the foam doesn't allow a very curved structure. to take
I see.
place.
Okay, yeah.
Whereas in ours, we can really unlock a very 3D profile. I wish I could show. When I see you next,
Yeah, no,
I think
yeah, it comes through on the video here. Yeah, I see. There's definitely more of a definitely a distinct like curvature to your guys' blade versus the other ones. That I don't know enough about aerospace to see how exactly that helps, but I can see there's definitely a distinct design difference there.
so. What this does is this was a small stage, and then we were able to apply it through like 7 different product ranges. So we have separate product design for uh, engine design. This is for electrical takeoff VTOL systems like vertical takeoff and landing.
Yeah,
So there's no one solution that fits all, but the manufacturing process is what allows us to entirely shorten that time and make it at mass volumes. Like our unit capacity to build is about 1,000 units a month, which is something an industrial partner would do, like say after a couple years of having that footprint in the market.
yeah,
So we had that advantage from the get
yeah.
go, and we were
That's
able to
amazing.
pilot it with a lot of companies and to have a turnaround time in terms of feedback very, very quickly. One of the only thing we were willing to give free samples if people were open to giving us feedbacks, right? And the ones we partnered up with, they actually had a lot of feedback to give, which helped us grow more each time we got that round of feedback, and it helped us understand that we've truly built something that's worth a lot of grain in this space, given now they're able to unlock into wider operating temperature range. And coming back to the passive de-icing, right, what this design now does is without any additional weight or power requirements or additional cost, we do this for all designs. It resists the onset of icing, which is very true if you think of all the drones. I mean, I envision an ecosystem where we will be operating all these systems come rain, water, snow, whatever. Like, you need
Yeah,
to be able to operate these systems all the time. No ambulance is going to be built on, oh, let me wait for the rain to pass.
right.
Ambulance needs
Yes,
to
yeah,
be done. So if that is the sort of framework and future we are looking at, we need to be able to build parts that can sustain that sort of format of flight. And we are building geared up towards that. So then the next segment was building motors.
so how exactly does it de-ice the propeller? So is it it's because it doesn't have the foam in it? What about that makes it
So
less prone to being icy?
So we actually worked with the manufacturers to alter the composition a bit, and
Okay.
also the design in itself. Like it's pretty steep, right? As you can see from a
Oh,
side
I see.
profile.
Yeah, so it just sort of like what flings the ice off, or
Yeah.
yeah,
So we simulated that over multiple designs and saw that with certain parameters, we could actually exercise it in at least the smaller ones, where it's a bigger constraint. You don't want your entire aircraft falling out of the sky. Ice
yes.
accumulation is pretty aggressive in like under 2 minutes. It's
Oh,
pretty
that
serious.
quickly it happened. Yeah, I guess it gets very cold up there, right? Yeah, that's
The right amount of precipitation, if
yeah.
there's even certain amount of precipitation in cloud, like in the ambient temperatures, and not ambient temperature, in the surrounding flight area, and you have like even a little bit of precipitation at the right temperature, ice accumulation can happen pretty quickly.
Okay.
So we ran that test, saw it, and then we were like, okay, we have like really good results. And now we are partnering up with as many institutional. It's one thing that you have technology that is like really great, but how do you convince others? Like it goes back to that question,
Yeah.
right? Like how do we get early adopters in place? So how we went about doing it is where I feel like I was very clever about this one. We partnered up with the biggest institute, which is like NASA equivalent in India, National
Uh,
Aeronautics Laboratories here. And they were more than happy to accommodate our product and test it out for us. We didn't want them to build it. We actually just wanted them to test it. And that would be an independent third party opinion. And they were so happy with it, they went ahead and like certified us for this category of flight.
and do they give you funding to like set up this factory to do all this prototyping, or is this just self-funded up to this point?
It's been bootstrapped up to this point.
Bootstrapped up to that point? Wow, yeah, it's because I mean, even starting a software product, which is much more lightweight, it's tough to find the time and money to commit to it. But manufacturing, I would imagine
It's a serious
everything physical takes a long time to do.
I think in hardware, in software, you can always have a next version of the like the software, right? You
Yeah,
can always update You can always take out the bugs next time. For
Right.
us, we have to change everything. Once molds are made, it's set in stone. That design is set. And for us, that comes after doing our iterative cycle of testing in field. You asked me, right? Like, how do we know if this design is valid or if I should take it off the shelf? We actually built a testing facility where we can do testing. Like, as much as I understand simulation and I did a lot of it in my educational background, I also am a firm believer as a pilot that I can believe things when I see them,
Yeah, that
you know?
empirical approach. There's the reality can't lie, so it's always good to confirm what it's saying. Um,
Yeah.
and
And we
yeah,
didn't want to do it like a closed room either. We actually built the facility out of literally middle of nowhere. It's like in middle of a
okay.
jungle essentially.
Oh,
And
really?
it's a 10 by 10 meter cuboid where it's a cage and we can do up to 500 kilogram system testing. That's pretty big. These systems support up, like the smallest one goes from like say 2 kilograms, so all the way to like 500 kilograms, both electrical and engine based systems.
Oh, and your motor and propeller, they're able to lift 500 kilograms off the ground?
I mean, not this, the test bed can sustain up to 500 kilograms.
Oh, I understand. Oh,
And
okay,
we
okay.
built, yeah, but
Yeah,
we built that too. Like, so that's the best part is that I have a very strong team. Whatever I envision is one thing, but I have a very strong team that's able to help execute that vision. And I think that's the entire mode here of what we are building. The team in itself.
and I want to get to the next component, the motor, of course, but just another quick question. So, how do you spin up a factory? How is that? Are you going to a factory that already exists and creates components, or is it completely from scratch?
It's completely from scratch. I actually even the first factory we built, there was not even a single fan in the facility, no lighting.
Yeah,
I've literally watched people install the ACs and everything. I know how the routing for such
incredible.
things are
Yeah,
done. Like I have literally we
and,
built it from ground up,
and
from
so
day
you're
one.
really relying on this this early domain knowledge that you got growing up around manufacturing to know like all the details that how to set that up.
Yes. And one of the things is like again, logistics are far different for a hardware and company versus like any other startup out there. Hardware means like the clarity in terms of how the operation is going to run end to end. It'll start from like having the raw material and to the final product, the quality check, everybody who's going to like be responsible, and we conform very strictly with the aerospace standard. And that's where I feel like my entire piloting background really came in handy, because I knew how closely the certifications for each and maintenance cycles for each were followed, and I had observed a lot of the A&P mechanics during my time at the flight school. I had seen fair amount of I have a fair amount of experience there, and a lot of my team members also came from like their separate experiences from aerospace companies, right? So when they joined in, there were certain structures they wanted in place as just part of the culture. Like, we are all going to do everything in writing. It's not going like digital documentation is part of it, but there's also going to be a hard, like, handwritten copy of everything.
Oh, is this like the
So
drafting up of the pieces and parts, like that kind of thing, like the old style drafting, or what exactly is getting
or
written up?
it's more like how each station finishes their work, right? They're also supposed to report like how they
I
got the
see.
part, and then
Yeah,
how they're sending off the part, what checks they did. And that's how you are able to do a quality control across processes, right? Then we know
each
exactly
stage you check. Yeah,
stage has been carried out the way we planned it. And it's in a way that everybody knows who is the next person getting what kind of product and what kind of stage you're getting it in, and what is your part of the job and what you will deliver next. So that
gotcha.
way there's a complete clarity of what your task is, and you get really really good at it. Repeatability in this space really makes them do better.
Yeah, yeah.
So
No, I would imagine that this in and of itself is a competitive edge, having this like ability to very vertically integrate the process of bringing this product to market. Versus, I mean, if I were to start a hardware company, I would just source all my products from different places, and I wouldn't understand the processes that led up to that point. So that's got to be a big advantage to have that domain knowledge. But yeah, so let's move on to the next component, the motor. I feel like you must have not built that from scratch, or is that from scratch too?
I think that was the longest research and development cycle we had. Like
Yeah,
we went through with the propellers, we had broken over 300 propellers to figure out and everything that we wanted to about it.
yeah,
But with the motor, even though we built like 13 versions of it by hand, each one was significantly different every time. When we do version changes, we do minor changes. It's not completely different in design. But to have 13 different motors each time, it was a whole, like, everything changes from sourcing to, like, setting up the process,
yeah.
jigs, fixtures, everything. And we didn't want to do it until we had reached all our targets. My team is very, like, decisive about that. Like, if we
Uh,
set out certain targets, we must meet all of them. They don't. And as much as I love that, I also, like, worry about that, because again, it's a time versus, like, delivery problem.
right. Like
But
don't let perfection be, or like don't let great be the enemy of good. I don't know if you ever heard that one, but yeah,
yeah,
if you focus too much on trying to make it perfect, of course, you might sacrifice actually getting it out there. But so when you say these targets, are they targets for just the motor itself? You're saying like parameters that you
yes.
benchmarks that you want to meet?
So for the entire module to be robust, right, we had already outlined certain requirements that are must-haves for each of the components that we are putting on that module. And hence, each of the products must deliver those targets. And with the motor, it was very necessary we did all of those. With the current design in the industry, right, one of the biggest challenges is that thermal management is a big deal to overcome, right? Everybody who's built the ecosystem, very simply put, if you take off and it's very energy heavy system, that means your batteries are running hotter in takeoff. Then when you're cruising, these hot batteries have not become completely cool. They're still hot, but not as hot. But now, when they come into cruise profile, they can still do it. But now, when they have to do the landing segment, which is another power or energy heavy system,
Yes.
energy heavy profile, now your temperature is shooting off. That means you need some cooling mechanisms in place. What we realized, if we want to truly unlock the next level of flight, we need to make sure that these systems are as small, as light, as robust, and also air cooled if possible. Like, we want to reduce down the complexity. Like, have you heard keep it simple, silly?
Yes.
The KISS
Yeah.
concept. I really like to stay by that. Like, if you keep it simple, sometimes they're just the right answer to it. And I think my team took it quite literally, and we unlocked something which is basically we have built world's highest continuous power density motors, which is beating or competing at least as like our power density goes up to 7.8 in continuous, which is what is competing directly with Joby and already beating NASA.
And so when you say power density, is this is the output of the motor over the weight of the entire motor?
It's more like how each gram of the motor contributes towards the power creation. So kilowatt per
Right.
kilogram is like the power per unit
Per
of
kilogram. Yeah.
yeah, the weight that is there.
Got it.
So if
And
the system
yeah.
is heavy, that means this number is going to be far lower,
Right.
right? And commercially, we see this range as like about 3 to 4.5. Like 4.5 is a push. Safran built their 100 kilowatt system, which got certified recently. It's a 3.5 kilowatt per kilowatt system, kilowatt per kilogram system. And we are talking numbers in all our design of upward of 6, like from the get go. So
So
that's a
sorry,
big.
that was your system that has 3.5
No, that's Safran's, which has built an electric motor and gotten it
oh, okay.
certified.
Gotcha.
Our So we built the smaller systems first, and that's a good way to, like, understand all the complexities in that come with the hardware, and then we map it to making bigger systems. Once we had successfully done it for the smaller systems, where we saw our power density range being from 6.5 all the way to 7.8, that's
Wow.
when we understood we had really unlocked something surreal, because now that means we are able to offer a significant weight reduction in the motor, which is not only air cooled but can now take on rugged aircraft parts as well. So this system becomes more robust, right?
Yeah, so that's a huge jump in efficiency there. How did you guys what changes in the motor did you guys make to achieve that?
So one of the key designs that we did changes, like one of the things is like the compositional insulation that we had at every stage. Somebody told me when at first we started building motor is all motors are good until their insulations fail. And
Oh, okay.
literally we focused there to the point that I was like, none of these parts can fail. And you can do that, but it's not cost effective for the bigger systems, right? Like for the smaller systems. I'm not saying they, like I said, like when we do prototypes, you can put all your heart and soul in building one prototype. But
Yeah.
to be able to make sure that it can be scaled to like numbers of numbers that will go to the masses, it's a very different math that you have to run there. And for us, from the get go, we had to keep that math in hand, where we understood that parts couldn't be exceedingly expensive or like rare earth magnets are like, say, only few areas have it. We couldn't have bottlenecks like, oh, I can only source it from one country. I should be able to source it from multiple places. I
Yeah.
should be able to like, so that way, that that is again dials back into design as well. These are manufacturing constraints, but they would come back in design too. So we kept going through that cycle over and over. But the biggest advancement we did, and we are filing patents for, is that we were able to make a heatless footprint. We actually did it for a client where we ran it at its maximum throttle. For other industrial partners, when they run it at 100% throttle, they give you peak power, which is the maximum it can be pushed for, and it only happens for like say 180 seconds or say like 200 seconds at
I
best.
see. Yeah.
Whereas ours was continuous. They ran it for 40 minutes and that performance didn't like fall short. Plus, it was cool to touch. They were the ones who took it down the podium. So we had inadvertently built heatless BLDC motors basically.
Yeah, the key to really in improving that power per kilogram was just improving, like there's all these constraints, different things you can change, but of course you have the manufacturing constraints and the design constraints, but you decided to zero in on the insulation, you said, in order to avoid overheating, and then that enabled you to have a higher load time where you're at max capacity or max output, and then to that therefore increase the power over kilogram, right?
Yes. And also, there's also compositional changes we went through. We worked with a lot of the suppliers to like enhance the compositions a certain way. And the insulations that we are talking don't traditionally exist, but again, had to be worked out with the manufacturers to see if they were scalable
Okay.
as an operational requirement. And they were able to meet out. Like these were very slight design changes that we went through. And essentially, we seeked path that was shortest for heat dissipation in the body.
Yeah.
Again, like magnets heat up, the coil heats up. How do you dissipate heat across the body? And we figured out what are the shortest paths for each of those and then built the design based on that. And hence, we were able to dissipate heat faster, even if it was generated.
Yeah, no, this is all incredible to even be able to do that and create such a gain in efficiency. When you're thinking about what different materials can better dissipate the heat, are you thinking through like theory that you learned in school, or is it more like just an intuition you built with working with so many materials when you were doing your composite research?
We actually went and learned from how other people had done it in the industry. We
Okay, yeah,
saw
no
like
shame in that.
everybody, I think understanding where everybody was failing was a big area for us to
Yeah,
overcome, right? Only then, as an early startup, we would have something really concrete to like, position ourselves technically and in hardware, but also push that boundary that, hey, we have a great product now. If I just say like, oh, I improved percentage by like 2%, that is great. That is still great. But it doesn't move that needle in a B2B business. It needs
yeah,
to be able to add more value. It has
right.
to be a serious value creation for any business to move their pipeline to yours. And it just can't be like, oh, it's a 2% efficiency gain. It needs to be pretty significant. And I
Right.
realized that in terms of money, it literally means like about 20 to 25% cost savings. Because you have to think about it from their perspective. They've already spent like years perfecting their procurement timelines,
Yeah,
logistic power line, like logistics segments, all of those things. They've perfected it. For them to move all of that to yours, it needs to have bigger value add, right? And
sure.
because of that reason alone, we knew that heatless is something that could really help eliminate, not only make the motor better, but also make sure that the systems that are being built down the line can be smaller. Right now, the biggest challenge is that we end up building very saturated systems. What I mean by saturated is that if you fly it in, like, say, normal surrounding areas, they'll fly just fine. But say I move that terrain even by another 1,000, 2,000 feet, right? The air density changes, platform is now performing differently, you see a loss in power. All of those adjustments have to be made in order to, like, adapt to the new environment. So that 2% value add has nothing to
Yeah.
gain in the system. It has to be pretty serious. So now when we are looking at bigger systems, thermal management becomes key. And if you, I don't know if you've ever looked at an aircraft design, first thing is propulsion, second is like aircraft structures and like, all of flight envelope and your speeds. You decide what your speeds are going to look like, you have a basic idea what your application is, then you'll choose a propulsion system complementing that, then you'll do like the aircraft structures, then you'll do avionics, and then you'll do its integration. All of these things make it so that the integration part is where you truly address a lot of the bigger problems like heat
Oh, okay.
management and like power inlay and all of that. And that's when I truly understood that if it is coming later that stage, that means somewhere people who were building this do think it should be minimal from the get-go. But that was not what we were seeing in the industrial trend. People were building systems that were very saturated, like operating at like very high percentage of throttle. That meant if you went even a little bit higher, you would cap out very easily because now the system was pushing higher percentage of throttle. Like you want to be as lean as possible, right? Like 40 to 60% of your throttle, which is where you get good cruise sort of profiles.
Sorry. Just let me make sure I understand this. You're saying it's better to have a motor and a system that can operate that maybe 40 to 60% of its capacity, and why is that? Just because it's less strain on the system, or
Yeah, because the more, so if it is higher percentage that you're
yeah,
at, throttle percentage, it's consuming more power. That means you're
okay,
fighting it's like you're resisting. The best thing is to be in the flow of things, but you can't help resist it. They're only, think of it this way, if you're decreasing the foot form, right? That means you're putting motors and controllers and propellers in a way that have to carry more weight at higher capacity, at like higher thresholds. If I
okay.
make a bigger system, then they are very lean. They can support it very easily.
So when you scale up, because
It's a
you're well
fight weight
within the
and power.
threshold, then they're not as likely to run into issues. Whereas if you were at right near the capacity and you scale up, it might surpass that capacity.
Yeah, so say if you're taking off with 10 kilograms, right? If you're making a quad rotor, you need an average of 2.5 kilograms per system. But do you want, like, there, you could have a motor that gives you maximum of 2.5 kilograms, right? But you
Hmm.
don't want that. You will want something that gives you a median, like a 40, like
I see. Yeah.
60%, so that you can take off very easily. Say if there is any gusts or wind or anything else additional that comes your way, you can work against that then.
Yeah.
If you're
Yeah,
at your
that
max
makes sense to
already,
me.
then you will, like, you will be capping out your system.
Right. Yeah, it doesn't leave you much breathing room for any kind of variability if you're right up against that threshold. So from that high level perspective, that definitely makes sense to me. Yeah. Do you have
So that's
something
why
else?
it becomes critical to like have a very robust system. If you design it for very high thresholds, then you have no breathing room, like you said.
Right.
If you design it in a lean way, then you have breathing room to do other weather, deal with other weather extremities. Not
I
extreme
see.
also. It very casually, you can have wind, you can have like some sort of anything come your way, basically.
Yeah, that definitely makes sense. And so you have the first component, the propeller, has a more of a curve, there's the efficiency gain there, and then you have the motor, the heat sink. The better heat sink allows it to operate more efficiently. And then on to the third part, the fuel cell. Was the fuel cell, was that something that you guys had to do a lot of innovating to try to make it more efficient, or was that out of the box more?
So the third one is actually the FOC controller, which
Oh, sorry,
complements.
I missed. Okay.
That's okay. The fourth component is the hydrogen fuel cell.
Oh, okay.
The FOC controller is pretty critical because obviously it's what sends signals to the motor how to correct itself for the right thrust values, right? Because it's a constant balancing game, right? And this is like done on a feedback loop system. It's how you finesse that and reduce the noise from surrounding, the better the system is. Very simply put, we basically worked on two areas of it, which is like again the heat aspect, and second, correcting and cleaning up the signal feedback because there are so many vibrations. So ultimately, the bigger challenge is also a lot of the designs that we saw in the industry were built in a way that they would push vibrations in their aerodynamic systems. What that means is like we have sonic areas, right? Like we have certain speeds we must maintain in design to ensure that we don't kick into like the areas of vibration. But because of the previous design and how they were manufactured, they ended up doing that. And because of that, the controller would overcorrect the vibration as like clean signals and overshoot each time. And that's why you would either lose the motor or the controller, or you would like, end up tampering the system quite a bit. Like it would constantly be trying struggle to balance itself basically
Yeah.
and not be in.
Okay. So you really want to absorb any external factors with this control system and make sure that the control system's not over correcting and then causing stress
Yeah.
and strain on the system.
Yes. So though that's like the entire module today, the propeller motor controller. And as a set, it works like an anchor for the aircraft's life. Once you've put it on, most people don't deviate from that system. And for us, that it was pretty important to understand that people are able to make good systems using our products. And one of the things we did employ was if I tell you I have a great product from get go, how will you believe it's great? You need something to compare with, right? And
Yeah.
that's why our first objective was to build industrial alternatives. So what people had already seen in hobby grade products, we offered same performance or better, but in the same sizes. There's a variety of sizes out there. We chose the most popular one and built our ranges based on those. And then we saw how our like collaborators were seeing performance change in their programs. So that's how we were able to map if our systems were really robust or not. And we had good feedback, so it means we worked well.
That's great. And so what was that product market fit? You said so a certain size was the best place to put it. Is that size a size that's used by certain products, like certain types of drones? Where did that place you in the market?
So actually, I spent a year, the year we were like finessing the motor, I spent while doing that. I was also traveling significantly across like 40 different countries. I think I went to over 42 countries to just attend different expos and shows all year round to
Yeah.
understand what was really out there. What India was doing is separate. Again, it's like trying to like build the ecosystem, so their learning is far different. Whereas
Right.
the world out there has like about 30 years behind them where they've built systems, they've used them, they know how it runs, they know what are like the pitfalls of it, they know what are the areas they want to improve into. So I basically wanted to see what's out there and dial back from there, like are we resolving all of the issues they
Yeah.
are experiencing in their advanced stages,
Right.
right? Like India is an emerging market, so it has its own struggle and they're looking at something different. Whereas the world now it's materializing as an ecosystem which is set to commercialize. We are looking at like drone deliveries, we are looking at flying taxis, we are even looking at like electric like aircraft systems, right? All of these are posing us to look at air travel in a different way. And if that is the case, what is it that they really struggled with? And what is it that really worked for them? So when I looked at those products, I actually understood there that okay, a lot of the design cycles were built with off the shelf products, and their limitations in terms of operation were capped right there. So that's how I knew that something like our product could really disrupt their operation, but also add key advantages in the areas they were struggling with. Like cold weather technologies is a big area of concern for all entities, be it commercial or defense. They're seriously looking at it. Similarly, operating temperature range. It's not always going to be sunny. It's not always going to be like really pleasant. It's going to have its own nuance. And with the current modules, that has been a challenge. So most people have done like policymakers have also done only visual flight rules. They haven't done beyond visual line of sight, which is BV loss operations. They're building those policies as we speak. And that's where I understood that even though the cycle has matured, the ecosystem is still slower than, it's much like how it would be for an aircraft, like an airliner aircraft, where the industry is slow to catch up with the new advancements that are coming in quickly. And
Sure.
I realized that's because there are a lot of moving parts. There's the regulators, there's the industrial partners, and there's the service sector that'll actually bring it out. So the communication between these three is very, very slow and
Hmm.
bureaucratic.
Right.
And
Yeah, that's unfortunate. Yeah.
it's unfortunate, but I think given that aerospace industry has been around for over 100 years, they have figured out what I love about this discipline is that across every entity there is a checklist. If you're doing a specialized system, there's a checklist even for that. Like
Right.
you want to do special testing, there's a checklist
Yeah,
for
no,
that.
I've heard that about like pilots will have their checklist. I don't know if that's just an industry. Yeah, yeah, maybe that. Yeah, it's part of the culture of aerospace just to check through everything and
And we,
if you're yeah
and
if you're
we look at,
trusting these machines, you want to make sure that you check everything right.
yes. So given how defined everything is, right, we want to conform to that ecosystem. So in
Yeah.
our own way, we want to build products that like conform very strictly to their standards, but also push their boundaries as well towards safer, better, long lasting systems. And the only way to do that is one is hardware, but second is also to convince them that we can do preventative and reactive maintenance using the modeling systems we now carry. Like the technology advancement today allows us to have sensor stacks on board, which can give you real time health monitoring information and all of those.
Is
And
that something that you guys built yourself, or is it you're layering it? Is it a third party library you're using?
so we are building that as ourselves right now, given the
Okay.
data that we have from other partners doesn't really coincide with the data we carry in terms of like the product composition is different. There's
Yeah.
a lot of those matrices that come at play, and in some way, because we are so young, that allows us to be that agile in terms of data collection. We have
Yeah.
different birds flying out different entities and different profiles of application. We have somebody who's flying in like 18,000 feet, and like the air density there is pretty thick. If you thought you had 100 kilowatt 100% of the power, you will only get like 60% of the power. That's a serious dump
Oh, I
just
see.
by being.
Since the air is thin, there's just not as much thrust from the propeller.
Yeah. So your
Okay.
propulsion system will now have to really push through. So very, very different prospects are there, and it's really exciting. Honestly, this is what allows us to pivot and think, okay, how do we make it really something that is real for tomorrow? What's being solved in India is probably like the extremities, right? Like the
Uh-huh.
coldest, hottest, humid,
Yeah.
most humid, and everything in the in the middle. But if you think about the other areas, say United States or European countries that are doing such operations, for them, even just having a product that lasts longer can change the unit economics significantly. Like batteries, for instance, right? They are supposed to give you 800 cycles, but they tap out in 200 cycles. You'd be lucky if you can push more.
Okay.
And so if that is the serious drop, having something like hydrogen fuel cell, which will give you over 2000 serviceable hours, it's pretty significant when you look at that. And this is where it becomes important to look at how the advanced system, like how advanced markets have looked at this. There's one thing to what is the true cost of owning a drone or owning an aircraft. I can run you those numbers, and I think it'll put a lot of things in perspective. In our flight school, this one guy got a plane for a Cessna that we were flying, a four-seater, for $170,000 at the time. Every year, like every 100 hours, he had to get a maintenance check done. Then there is an annual review which requires $25,000. So
Wow,
by
yeah.
his 13th to 14th month, he had already exceeded $170,000.
That's tough. Definitely a burden to any kind of aircraft that you have. Yeah.
Yes. So if you look at it, what we realize, the one-time cost, which is where people in emerging markets are more focused on, makes up only about 10 to 15% of your true cost. Whereas the bigger cost comes from your maintenance, repair, overhaul, and logistics. Those are the two bigger areas. MRO makes up about like 35 to 55%, depending on which part of the world you're in. Similarly, depending on the minimum working wage, logistics, like, cost of the pilot, travel logistics, transportation, all of those, subscriptions, insurance, all of these things come part to it, right? And that's when you understand that they have a bigger contribution in assessing your cost per flight than just the cost of the aircraft itself.
Yeah, that's a lot to. Is that factored? Are those external factors? Is that factored into your design as well? Is that yet another constraint on the design?
No, so that's why it's very important for us that the serviceable hours are at least double or triple, right? Like it has to
Yeah.
add value in terms of bringing this system on board. And for that reason alone, our biggest milestone, I think, which I have not said so far, is because they're agnostic of size and scale. This is the first time solutions are applicable from drones to flying taxis to aircrafts, which is not true for any other product line. If you see, if you look at somebody like Hudson, they've only focused on building propellers, but for certain categories. If you look at like DJI, they've also built parts only for the drones, and like they have not built parts for flying taxis. So for us to be able to cater to all three segments is a big deal. Our biggest proof of concept that we have done is a 96-inch tri-blade, which is for a
Wow.
five-ton aircraft, and a 950 horsepower system, which is the
That's
biggest.
amazing.
And we are set to quadruple the life serviceable hours for it. And that means the unit economics would really change, because if you've ever seen any defense contract or any airline contract, the cost of the plane is significantly lower compared to the MRO contract because it's
Okay.
time bound. It accounts for a lot more different numbers. If we are able to optimize the entire MRO segment, there is significant cost savings there.
Sorry, why are you guys able to be size agnostic and scale up and down like that? Is that's because of your design?
Yes. It's because of the design and the way we manufacture. We've had significant advantages on both systems. And the team is not from a traditional background of building these systems, right? So they question everything, which is the best part of it all. I
Yeah.
think one of the most intrinsic part of building is when you start building in this ecosystem, it's like you start working under the constraints that are not yours, but by the industry's previous experience. I also think it goes hand in hand with understanding what were their limitations at the time versus what are those limitations today. Have we really evolved, or are we still at the same stage?
Yeah.
How can we push those boundaries is like what we are assessing constantly, and those little breakthroughs help us do better each time. I think that's where the cycle really pushes through. Like my CTO, he constantly challenges traditional methods, and because
Uh,
I've flown and I know the industry, we will have like a battle round of things like,
yeah.
okay, this is how it's done before. And I said, why not this way?
Right.
And we constantly do it. But how we are structured as a startup is also very different. We have 4 team members that are core to the entire program. I primarily do the literature review and seek out what are the products we need to build to be able to make ourselves distinguishable in this industry. Because again, it's like old people industry, right? I don't I don't have a better way of putting this, but it's like I'm the youngest person in the room every time.
Right. So it's
Like
really ripe for disruption. What do you find like what's the highest in demand product right now, would you guys say, as you're entering the market? Is there a certain throughout that scale of size, a certain size that you're seeing the most demand for, and what is that? What are they building? Is it drones? Is it what is that?
It is actually drones, but manned
It is
ones. So
drones.
they want to be able to do, most of the companies we've seen is what they want to do is build cargo systems with the
Yeah.
same payload capacity and then later be able to replace that with like manned passengers basically. So they want to do a capacity check using cargo logistics. And
Okay.
then once that operation is in place, they then want to move to manned systems. So the biggest ones we have seen currently in the order for the defense company we worked with, it's a listed company in India. They use like 40 inches propeller, which is a 1 meter propeller.
Wow.
40
And
inches.
sorry, there's four propellers, or is it a quadcopter, or is it just a single one?
They have multiple design. Their
Okay.
design is like a eight, like coaxial, like top and bottom, four.
I see.
So they do like eight motors and eight propellers, basically.
Wow.
That's all. Essentially, everybody is trying to make this a very compact, because in India, there's no infrastructure at the end of the day. We don't like recreational flight, which is something I truly enjoyed in US, is not something I'm able to tap into India because again, the infrastructure is not catering to that, right? The airports
Mhm.
are more for like, public usage and things like that. It's not meant for like, recreational purposes here.
Yeah, I was going to say, so yeah, you're taking all this information from the manufacturing, the design, the regulation, how ready the ecosystem is for these products, what the demands are on the customer side. What do you see? What's your vision for the future for this? Both, I mean, your own products, but also the industry. Where do you see things going?
I mean, think about it. How I think about this problem is second to sleep and work, we spend most of our times in our life in transit. I want people to
Uh-huh.
be able to do better things than doing transit.
Yeah,
And and helping them unlock that would be only possible through air travel because roads are set in the ways. It's a 2D structure. Whereas
right,
if you do fly air travel, A to B becomes faster, easier, and we can do multiple layers of it. So I do see air travel as a solution to saving ourselves one of the most valuable thing, which is time, right? We want to
yeah,
be able to enjoy lives and do things we want to do. But if you have trouble even getting across the city, right, then you're
right.
not going to be able to do anything. And I think like it also, like somebody explained, I can't remember who said it, but think about it this way. If you are struggling to get to the place of work, right, your struggle started so early on that your mind cannot completely be at workplace either. That's why like I at least want to help people unlock scalable and affordable air travel. And doing that, we would be then able to unlock, say, ambulatory systems that are operating like cloud systems, right? Like in India, I'm sure you've heard of like 10-minute delivery, right? They have
Uh,
cloud warehouses in the back where they manage everything, and it's like a central space to each of the location. Similarly, if we were to impose the same ecosystem in, say, healthcare for ambulatory support, a lot of the drugs which need cold storage in India specifically, doing that sort of management is really hard. And having that sort of ambulatory support or like search and rescue operation, even anywhere where there is time efficiency and human life at risk, we'd be able to solve all of those problems right away. And I think there's a lot of systems we do end up doing those even manually to this day when we have advanced systems, but that's because of the cost, right? So I do think cost is equally a part of the problem, and so we need to be able to solve all of them. So it needs to be scalable, it needs to be affordable, it needs to be accessible. So
yeah,
while everybody is focused on building the bigger systems, I'm more focused on making sure that for these systems, there are enough parts out there to get to that stage. And that's
right.
how they will really unlock that bracket of innovation.
Yeah, I'm currently reading, and I've mentioned this in some past episodes too, but a book on Nikola Tesla, and one of the things that he did, a great inventor, of course. He created a very good oscillator, just a component, an oscillator, and it was used in so many different inventions that other people made, businesses, in radio, in power, supplying power to people. And it was just this very well built single component that was very robust and under so many constraints was able to perform well. So it reminds me of your component that you're building that will unlock for so many other people building businesses um, to to create those businesses and create products that provide value to people. So I think that sounds like a very fascinating uh, strategy to go with.
One of the things I haven't touched here is also that the team that builds, right? Ultimately, I can envision a whole lot of things, but to be able to execute actually comes from the team that, believes that this can really happen. And
Yes.
that kind of reality check is constantly needed. But one of the strongest thing that I have going for me is that my team's mindset is every time we hit a wall, their intuition is not, oh, like let's ditch the whole thing. They'll be like, okay, why can't we do this? What does it take? And if it's a
Yeah.
machine, say if it's a machinery that has not existed, we have actually ended up building machines for it. We've built
Yeah.
machines to that point that at this point in time, I'm just confident in building anything. Like, I know that as long as it fulfills a purpose, I know my team can help me bring that product to life. So that's there. But also, the most interesting thing about the entire team is all of them individually have overcome so many challenges in their own and personal lives that it reflects in the work they do. For them, every day is like a do or die situation. It's like,
Uh,
and even when that's not the case, right? Like,
yeah.
we're
Yeah.
not such a such a space. But in 2.5 years, if I reflect on it, like as I was building my deck, I'm looking to raise this year. In 2.5 years, we've done over 60 products. We've
Wow.
done over 25 pilots. We've built everything ground up. There's been no support whatsoever. We've also gotten like certified by industrial partners, academic institutions, and we are doing it globally as well. And we are now looking at different bigger systems as well. So what made me realize is, and the team that manufactures it, right? One of the bigger challenges we are trying to overcome in India is there is no women in manufacturing, which has
Hmm.
been something like, I'm a woman myself, right? I knew what it took to get where I am. I know the
Yeah.
battles I've, but I also understand it's empowering to be able to support yourself through work. Work can be such a big space of validation of who you are as an individual. And I'm seeing that. So we actually hire locally from the neighboring villages who have no idea how to work with
That's
composites.
great. Yeah.
And then we train them. That's on us. Like, that actually like delays our cycle. I could obviously hire, but I also know the responsibility to upskill the entire ecosystem and be vocal for local is equally important. So
Vocal for
wherever
local. Yeah.
yeah, like wherever I build, I want that community to be able to thrive. I want everybody to be able to move together. There's no race in which there's a single winner. This is one race where we all need to come out winners. Only then it's going to be something valuable. So actually, all of these parts that you see have been built by people who have no experience in composites. They have literally been trained on ground for 3.5 months, and they have such a big thrust to prove themselves that they give it their best shot. And I would rather put my bet on these people
Uh,
than anything. I think that's what makes it so valuable. And the fact, like, now they all have like a space of belonging, things that they have built. They have things to reflect on, right? Like, that's a bigger community building that we are doing now as an entity. So I think that culture set is equally important. And then having a strong team that like helps do that is the most important of it all. So I think that's where we are at. Like, given the current stage, we've built the products. Next, we are looking at certification, and then moving to the next stage of the product, which is equipping it with advanced sensors, getting involved with the communities worldwide, and then bringing them on board in a big way.
yeah. Wow. Doing all this, the manufacturing, the designing, everything, all these components, and also training people that have no experience in this area as part of a pro bono effort. That's just even more incredible. And I'm sure throughout this process, you must have faced many incredible challenges. Is there one last before we sign off here? Is there one last thing that you would advice that you would give? Let's go with specifically advice for someone trying to get into the deep tech hardware space, the advice that you would give to them when trying to navigate all these numerous hurdles?
My advice would be that if you have figured out that there is a problem to be solved, at least try it out. It's worth a try. If other people thought they could resolve it, they would have already done it by now. So don't let that be the limiting factor. And again, prototypes that don't make art to the masses add very little value, because it'll be great for a paper, but if it doesn't come more like materialize into a prospect that other people can use, then it's just deep research. It's not concretely adding value to the community. Like, have that distinction very clearly mapped out for yourself, which way you're going for, and the assessment that you will carry out for each of those will be very different. If you're just building for the sake of building, it's very different. If you're building so that it reaches the consumer, your outlook will be very different, because it will be oriented from their perspective and not what you want, what you think they'll need. It's what they need that you need to build and resolve. That's the nuance here.
Yeah, no, it always gets down to the customer problems. You got to be solving real world problems and be able to scale up your solutions to those problems. Well, Shreya, it's been an absolute pleasure talking with you. There's an idea in software that any kind of thing that you might want to build in in the logic data space, it's possible to build, because we have these computers. They can abstractly create any kind of logic, manipulate any kind of data, but the way that the way that you're talking about manufacturing and making stuff in the real world, it started to make me think that, there's a possibility to have that kind of perspective in the real world with actual material things, to be able to have such a control and command over them, and through a lot of hurdles and struggles, but to really be able to make something out there that is exactly to the specs that you need in order to do whatever it is that you're trying to do. So absolutely, yeah, fascinating conversation and great story. And I look forward to seeing how the aerospace industry develops with disruptors like your company.
Thank you so much for having me. I honestly believe, like, at the end of the day, if you can see the beyond, just chase it. It's worth a try to like push that beyond limit, and rest of the things will work out. Like, you have only one life. I at least want to keep doing what I love doing.
Right.
Like, it's a privilege, and I respect all of that. I embrace it with everything.
Absolutely, yeah. You have one life, spend it enjoying pursuing your interests, not nothing else. Yeah, I love it. All right, well, thanks, and I look forward to down the road talking again once you guys have gotten even more products off the ground. Thank you.
Thank you.